So thank you for inviting me to give a talk. Yes, I'll be talking about sum of squares proofs for Log-Sobolev inequalities. And this is joint work with Oisín Faust, who is a PhD student at my PhD student at Cambridge. So, okay, so the main motivation of this talk is to study Markov chains or mixing times of Markov chains. So we're given a certain transition matrix or a Markov kernel on a finite state space, X. So this means that Kij, I mean, the entries are non-negative and the sum of the each row of K is equal to 1. So the Kijs are transition probabilities. Okay, and we assume that we have a certain invariant distribution pi. Okay, so this means that if your initial distribution is pi and you apply one step, essentially you stay at pi. So this means that pi is an eigenvector of K with eigenvalue equal to 1. So a left eigenvector with eigenvalue 1. And so what we would like to study, I mean, the main question that we'd like to study is the continuous time Markov process associated to the transition kernel K. And so this is given by this differential equation. So you start with an initial distribution on X, P of 0, and the distribution evolves according to dP over dt is minus PL, and L is the Laplacian associated to this kernel K. And the main question of interest is how fast does P converge to pi, to the stationary distribution pi. Okay, and so there are many answers to this question, depending essentially on how you measure the distance or how the distance from P to pi. Okay, and so the classical way of doing this, which leads to ideas based on the spectral gap or spectral theory, is to study, for example, the variance of the density function. So the density function is just P of t divided by pi. So this is the density of P of t with respect to pi. So this function, its expectation is equal to 1. And so in the limit, when t goes to infinity, when P of t converges to pi, this function will be constant equal to 1. And so by measuring the variance, we get a measure of how close we are to pi. Okay, so we want to understand how this variance of this function f of t converge to 0. So if you by using the evolution equation for P, one can derive very easily using the chain rule the evolution of the variance of f of t, and what you get is that the derivative of the variance is the negative of this quadratic form. I mean this so-called Dirichlet form, which is just the bilinear form associated to the Laplacian L. Okay, the Laplacian I introduced in the last slide is just identity minus k. Okay, so you can show that we have this differential equation for the variance. And so this is where the Poincaré inequality comes from. If we're able to bound this quadratic form in terms of the quantity that we're interested in, so the variance. So if we're able to show that E of f, so this quadratic form is bigger than lambda times the variance, then we're able to get a differential inequality, which we can integrate, and then we get that the variance decays like the variance of f at 0 times the exponential of minus 2 lambda t. Okay, so the Poincaré constant lambda is the best possible constant that you can get in such an inequality. And in this case, this constant is just an eigenvalue, can be computed by just an eigenvalue computation, because this is a quadratic form and this is another quadratic form. Okay, and so it's not very difficult to see that the best lambda here is the second smallest eigenvalue of the Laplacian. So the smallest eigenvalue of the Laplacian matrix is 0. This is because K has a K pi is equal to pi, and so the second smallest eigenvalue is the Poincaré constant. Okay, so from the computational point of view, this is easy to get. So I mean, this inequality is okay. Gives us an estimate of the mixing time of this continuous time Markov chain. But so sometimes, I mean, one would like to measure distances in a different way, so the convergence in a different way, and this is where the Log-Sobolev inequality comes into play. So So the Log-Sobolev inequality is something that looks like the Poincaré inequality. So we would like to lower bound also the quadratic form, this Dirichlet form. But instead of having a variance on the right-hand side, what we have is a certain entropic term here. So instead of having the variance, we have this summation over the invariant distribution pi I times xi squared log of xi squared. And we want this inequality to hold for any x that lives in the unit sphere, so with the weighted by this pi I. Okay, so the largest alpha force, this inequality holds the logarithmic Sobolev constant. And if one has such an inequality, then one can bound the KL divergence of P of t and pi in the following way. So it's less than the initial KL divergence between P of 0 and pi times an exponential minus alpha t, where alpha is the log-Sobolev constant. Okay. And so, I mean, the reason this is sometimes much better than the estimates in terms of the variance is usually because the constant in front of the exponential depends logarithmically in the size of the state space rather than just I mean linearly or polynomial. So so this is why log-Sobolev inequalities are I mean estimates based on the log-Sobolev inequality are desirable, but on the other hand, from the computation point of view, whereas computing lambda, the Poincaré constant, is just an eigenvalue problem, so it's fairly easy. Computing alpha is much harder. Okay, so in fact, alpha is only known exactly for just a handful of transition kernels K. So what I would like to do in this talk is to address the computational question of how do we compute or how do we get lower bounds on the constant alpha given the input kernel K. Okay, so in the rest of this talk, I will completely forget about the motivation coming from Markov chains and probabilities and so on. I will just consider the computational question of given a certain input kernel K, so just a matrix, and its invariant distribution pi, I would like to compute a value alpha, the best possible value alpha, such that the inequality that you see at the top here is true. Okay, so I will just focus on this computational question, and essentially we'll give an algorithm that will give us a formal, strictly a formal lower bound for the logarithmic Sobolev constant of H. Okay, so to start, I mean, I would like to, before talking about the log-Sobolev inequality, I would like to talk in general about the problem of proving inequalities. Okay, how do we proving inequalities from a computational point of view? How do we do this? Okay, and I will start with the case of polynomials. Okay, because this is the easiest case, and then I will go back and see what I will talk about, how it applies to the log-Sobolev inequality. So the question I would like to consider here is, given two polynomials p and q in n variables, I would like to decide the question: is the polynomial p of x non-negative whenever q of x is equal to 0. Okay, so q here defines what we call an algebraic variety, so the set of x such that q of x is equal to 0, and I would like to understand whether p is non-negative on this set. Okay, so this question from a computational point of view, this question is hard in general. Even if q is, say, a quadratic, defines just the sphere, this question is hard in general. It is decidable though, so there is a finite algorithm that can decide this, but the best algorithms we have currently have a very high computational cost. Okay, so there is, however, a certain way that one can certain sufficient conditions that are tractable and that allow us to prove such statements. And this is what we call the sum of squares proofs or sum of squares certificates. And the idea is very simple. So it goes as follows: if I am able to express my polynomial p as a sum of two terms, so as a certain polynomial s of x plus h of x times q of x, where h here is an arbitrary polynomial and s of x is a polynomial that's a sum of squares, okay? Then I claim that the statement is true, then namely that p of x is non-negative whenever q of x is equal to 0. Okay, and this is obvious because if I take a x for which q of x is equal to 0 and I plug it in, I get p of x is equal to s of x, and s of x is the sum of squares, so it's a non-negative. It gives me a non-negative number. Okay. So just to make this this kind of concrete, I mean, if you take the polynomial p two variables x and y, it's just 1 minus x. This polynomial is non-negative whenever x, y lies on the circle, so defined by this polynomial. Okay, and so what's the sum of squares proof of this fact? The sum of squares proof takes the following shape. So p is equal to s plus hq, and here it's not so hard to find expressions for s and h. So s, for example, you can take it to be this sum of squares, and h is just the constant 1/2. Okay, so that's a sum of squares proof of this following simple fact that you see here at the top. Now, the key point is that the key fact that we're going to try to leverage is that one can search for a sum of squares proof efficiently. So we have efficient algorithms that allow us to search for sum of squares proofs, and algorithms are based on semi-definite programming. Okay, so I won't have the time to explain exactly how this works, but essentially the idea is that if you think about the set of polynomials that are sums of squares, so this is a convex set in the space of polynomials, and this convex set has a nice representation. So there is a nice, what we call a semi-definite representation of this convex set that allows us to efficiently optimize, for example, over this convex set. Okay, so we can test efficiently membership in this convex set, we can do separation, we can do optimization, and so on. Okay, and this is kind of, here I put the more detailed statement here is that a certain polynomial S is a sum of squares if and only if there exists a symmetric matrix Q of size, so this big N is the dimension of the, so essentially is the number of monomials in n variables of degree d over 2, such that the for each coefficient of the polynomial S, I have a certain linear equation. And so the main thing to look at here to note in this linear in this equation is that this equation is linear both in S and Q. Okay, so not only for a fixed polynomial S I can decide whether it's a sum of squares, but I can also search, I mean, for a polynomial that's a sum of squares. So in other words, the S gamma can actually be variables of my optimization problem as well. Okay, and this will be very useful for us because we'll be searching, when we search for a proof, the polynomial S is an unknown, so it's also a variable of the, it's a variable in the problem, in the decision problem or the optimization problem. Okay. So now, okay, so this is very a brief overview of sums of squares. So let's now go back to Log-Sobolev inequalities. So this is what I would like to do in a Log-Sobolev inequality. I would like to, I have my Dirichlet form, I have my entropic term, okay, I just call it B of x. And I want to show that this is non-negative for all x in the sphere. Okay, so I'm going to assume first that someone gave me an alpha and I want to see if it's a feasible one, but we'll actually see very easily that we can also just search for alpha in the optimization problem. But just to fix kind of ideas, let's assume alpha is given. So the main problem, I mean, I cannot directly apply the sum of squares. I cannot directly search for a sum of squares proof of such an inequality because B of x is not a polynomial. Okay, so B of x involves certain logarithmic terms. Okay, and so I cannot hope to write this left-hand side is equal to a sum of squares plus another polynomial times S of x. Okay. So, okay, so the approach that we're going to take is a very simple one. It's the most natural thing. So what we're going to do is that we will try to find a polynomial, another polynomial b hat, okay, that's an upper bound on B of x, okay, this entropic function, and we'll attempt to prove a certain stronger inequality instead, okay, and the stronger inequality is the one where I replace B of x by B hat of x. Okay, so if I'm able to prove this inequality with the sums of squares, then this also proves the Log-Sobolev inequality with the same constant alpha. Now the question is, of course, how do we choose B hat of x? And so I will describe two ways to choose B hat of x. The first one will be based on certain Taylor expansions, and the second one will be an adaptive way where we let somehow the optimization problem is search for the best possible polynomial upper bound on B of x. Okay, so I will explain both of them. Okay, so the first one is based on a very simple observation that if you take the function, if you take this entropic term, just one term of it, so just the term t squared log t, if you take this function, which is just a function of one variable, and you do the Taylor expansion of odd order at t around t is equal to 1, what you get is a polynomial that's an upper bound on the function everywhere. So it's bigger than t squared log t everywhere for all t. And so what this allows us to do is to take this function b of x and to replace the terms xi squared log of xi squared, okay? And we replace this by the Taylor expansion to an odd order. Okay, and this gives us a polynomial that's bigger than b of x. And so we can, and then we can use sums of squares on this upper bound. So then this gives us, we can then write a semi-definite program or a sum of squares program, I could call, that will give us a lower bound on the Log-Sobolev constant. And so it looks as follows. So the variables, so essentially this is the key maybe constraint. So I have on the left-hand side, I have this Dirichlet form minus 2 alpha hat times, so this is the b hat, so this is the approximation or the bound on b of x that's a polynomial, and I want to write this as a sum of squares plus a certain polynomial times the sphere constraint, okay? And so the variables here are really alpha hat, so the best constant that I'm looking for, and then s of x is a sum of squares polynomial and h of x is a multiplier. Okay, so this is a semi-definite program, and so one can actually solve this problem efficiently, and then the solution of this problem will actually give me a lower bound on my Log-Sobolev constant. Okay, so in fact, I mean, this bound, even though it looks fairly natural, this bound already can give us non-trivial results on Log-Sobolev constants. So just to illustrate this, if you take the simplest possible Markov chain, so on two states where you kind of transition to, you stay or you transition to the other state with probability 1/2. Okay, so it's known that the Log-Sobolev constant is equal to 1/2 in this case. And this corresponds to proving the following inequalities. The following inequality, so here on the left, you can see this is the Dirichlet form. And this is this b of x with the x squared log x. And you want to show that this is not negative for any xy in the sphere, okay? So what you do is that if you use a Taylor bound of degree 3, and then so you replace the entropic terms by the corresponding Taylor polynomial, what you will get this left-hand side will be then a degree 3 polynomial in x and y. And then, okay, so I simplified it, and at the end what you get is the polynomial on the left-hand side that you want to show is non-negative, again on the sphere, okay? And so this yellow inequality is stronger, so implies the blue inequality. So if I'm able to prove the yellow inequality, then this implies the blue inequality. And now I can attempt to prove the yellow inequality using sums of squares, and indeed it's not so difficult to do it. So you can find S a polynomial that's a sum of squares and H a multiplier polynomial that certify essentially the non-negativity, that certify the yellow box here, the yellow inequality. Okay. So here you can see that I've used the sum of squares term is here multiplied by 1 plus x plus y, and not just by 1 as I had in the previous slide.
I've been paying attention to your talk and not the clock, but we're getting close to two minutes here, so I should have told you sooner. Sorry.
Okay, no problem. Yeah. So okay, so maybe let me then go on, since I only have 2 minutes. Okay, so the other approach is based on an adaptive way to look for the upper bound on the entropic term. And so the idea here is to have p hat, so another polynomial. Instead of putting the Taylor polynomial, we put another polynomial p hat, and this p hat is a variable of the optimization problem. And so we add a constraint that we want that p hat is an upper bound on t squared log t. Okay, so this is not directly solvable exactly, but we can do. We can do something quite close to it where essentially we replace the log by a certain rational approximation or rational upper bound on the log based on Padilla approximation. These are very good approximations of the log. And then we impose this constraint by a sum of squares, again, by another sum of squares constraint, but a sum of squares constraint on the real line. Okay, so essentially, so this more adaptive way of looking for a polynomial upper bound performs in general much better than the Taylor bound. Okay, so maybe let me move on. So okay, so this is essentially what we propose to get bounds on the Log-Sobolev constant. So there are certain issues related to getting formal proofs from floating point solutions of the SDPs. So you have to take the solution of the SDP and round it to a rational number and so on. So this is all done. We have kind of done this part of the work. And this is all implemented, in fact, in the, my student Oisín implemented in the Julia language. And so it's available at the following URL. So you can, the idea here is that you just define your transition matrix K as a set of matrix of rationals and the invariant distribution, and it will give you a rational number, which is a lower bound on your Log-Sobolev constant. So maybe just to finish, two examples. So we tried it on the complete graph, so the simple random walk on the complete graph. Here the Log-Sobolev constant is known, so we can see that our method produces bounds that are very close to the actual value. So this is the error that you see on the right here. So this is one example, and the second example is a case where the Log-Sobolev constant is unknown. So this is the case of the cycle. On the simple random walk on the cycle, the Log-Sobolev constant is known for all even n and for n is equal to 5. And it is an open question whether the Log-Sobolev constant is equal to lambda over 2 for all odd n bigger than 5. Okay. And so we actually managed to, using our method, we managed to give a formal proof of this for all n of odd order up to n equal to 21. Okay, and so here we use some additional specificities of this kernel K, which is the symmetries. We exploited the symmetry to reduce the size of the SDP and so on. Okay, so this is the end of my talk. So there is a paper online at the archive that we just put, and there is a link to the code also in the archive paper. So there are certain multiple open directions that one can investigate. So one, for example, is to consider the problem of the fastest mixing Markov chain. So the question of finding, a certain Markov chain, so a certain transition matrix K with a particular support that has the largest Poincaré constant. So this problem was considered in a paper by Boyd, Diaconis, and Xiao. One can consider the equivalent problem where we want to maximize the Log-Sobolev constant. And so this can be done using our approach. I think an interesting question is to study the difference between these two objective functions. Two other obvious open directions are to get a relaxation for the modified Log-Sobolev constant and obviously for the quantum modified Log-Sobolev constant. Okay, so thank you for your attention, and I'm happy to take questions.